My name is Lim LEE from KGSEA Math Circle, and today I'll be covering a basic geometric and algebraic concept known as trigonometry. Because this method of solving problems is a prevalent one in competition math, I'll first give a general overview of the topic and dive straight into some competition problems which utilize trigonometry. So to begin with, let's get a general overview of what trigonometry actually is. Trigonometry is a branch of mathematics that focuses on understanding the connections between the lengths of sides and the measurements of angles in triangles and various other geometric shapes. It's valuable for solving practical questions, such as determining the height of tall objects like trees or buildings, without needing to measure them directly. Additionally, it can be used to calculate distances, like figuring out how far a ship is from a lighthouse based on the angle of elevation. Trigonometry is rooted in three fundamental functions, namely sine, cosine, and tangent, denoted as sine theta, cosine theta, and tangent theta, where theta is the angle. These functions are derived from the relationships involving the sides of a right triangle. In the accompanying diagram on the bottom right, the sine of angle theta, which is the angle of elevation, is defined as the ratio of the length of the side opposite the angle to the length of the hypotenuse, while cosine is defined as the ratio of the length of the side adjacent to the angle to the length of the hypotenuse. And finally, of course, tangent is defined as the ratio of the length of the side opposite to the angle to the length of the side adjacent to the angle. It's evident that these ratios depend solely on the magnitude of the angle theta formed by the adjacent side and the hypotenuse. And additionally, there's some useful information to note here that tangent theta is equal to sine theta over cosine theta. Now, let's clarify the concept of circles and radians in trigonometry. The unit circle, a circle of radius 1 on the Cartesian plane, serves as a crucial part in understanding the function graphs. We can visualize a line within the circle. Starting from the center and extending to the circle's edge to point P, and an angle theta, which is formed between the hypotenuse and its intersection with the x-axis. You can then state that this point has the coordinates of cosine theta, sine theta. And this is because the line's height relative to the x-axis is represented by the sine of theta, and correspondingly, the adjacent side is equal to cosine theta. It's important to emphasize here that in the context of trigonometry, we use radians to measure angles. If you're new to radians, remember that pi radians are equivalent to 180 degrees. And so correspondingly, we can express other angles in radians as well, such as 30 degrees and 45 degrees, which equals pi over 6 radians and pi over 4 radians, and so forth. Radians are used in trigonometry because it is easier to connect trigonometry to algebra and geometry, and this concept will be explored further in the following slides. Here, we can see a graph of the functions of sine, cosine, and tangent on the unit circle. The respective reciprocals of these functions are the cosecant, secant, and cotangent values, which are plotted here as well. There are three characteristics that we can notice from the following diagram. The first is how all of the functions are repeating, or going back to their original values, with a frequency of 360 degrees, or 2 pi. Additionally, we can also see that the values of sine, cosine, and their reciprocals, cosecant and secant, never exceed 1 or go below -1. And finally, the functions of tangent and cotangent go to infinity and 0 when the moving radius crosses the x or y axis. The sine, cosine, and tangent graphs, when plotted on the Cartesian plane, correspond to the graphs shown on the left. We can see from the representations that the graphs oscillate or cycle with a period of 2 pi. And while sine and cosine graphs never pass 1 or -1, tangent goes to infinity, just as we saw in the unit circle. Additionally, we can also derive a few important formulas from these graphs, shown in the bottom left corner. Remembering again that pi radians is equal to 180 degrees, these formulae are easily understood by taking an example. Let's say 30 degrees in this case. In this diagram, 30 degrees is here, and 180 minus 30, which is 150, is here. So we can see, obviously, that the values of y equals sine 30 and y equals sine 150 are the same. However, cosine and tangent have two additionally inverse values. Now, the top right has a visual of the sine graph drawn from the unit circle as well, where the height of the rotation radius is plotted on the plane. For competitive math problems, it's useful to memorize the formulas on the bottom right. The sine, cosine, and tangent values for 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees will help you a lot because they're the most commonly used in competition problems. We'll be using these problems in the problems later on in the video as well. It's also useful to note here that tangent 90 is not defined because if we remember, by definition, tangent is equal to sine theta over cosine theta. But if cosine theta is equal to 0, then we can't define it because in math, dividing by 0 usually leads to bad results. Now, before we move on to some competitive problems, there are some basic formulas we should know. And one of them is known as the sine addition formula, and I'll now explain this theorem with a proof without word solution by Sidney H. Kung of Jacksonville University. I'll give you a few seconds to read it over, and I encourage viewers at home to try and make sense of this diagram on your own too. I think that was enough time to at least get a grasp of what this solution is trying to prove. And the first thing we should note down here are some observations. The first observation is that there's a triangle with side lengths ABC and angles XYZ respectively. We can also see that the circumradius is 1/2 by looking at the second line of the proof. The second observation is that the perpendicular bisector from the radius to chord C, from the center of the circle to chord C, forms an angle of Z. This is proved by the properties of a circumcircle, where the circumcenter connected to points A and B equals 2 times the angle BCA. And so after these observations, we can go straight into analyzing this proof. The first line states that C is equal to A cosine Y plus B cosine X. And this is proven by the cosine definition on triangles CBE and CAE. We can see that the cosine angle X is AE over B, and cosine angle Y is BE over A. And therefore, if we multiply A and B respectively to these cosine values, we get AE and BE, which sum to AB with a length of C. The second line then states that sine Z is equal to C over 2 over 1/2, which is equal to C. And we can prove this by looking at triangle OAD. Sine Z is equal to DA over OA, which is equal to C over 2 over 1/2 calculated as C. Similarly, we can denote sine X as A and sine Y as B with the same methods. Finally, the third line states that sine X plus Y is equal to sine pi minus X plus Y, which we know is true by the identities we saw on the previous slide from the sine X graph and function. This is equal to Z as pi is 180, and because the angles of X, Y, and Z are corresponding to the angles of A, B, and C, they all sum to 180. So as A is sine X and B is sine Y, this formula can be proven in the third line, where the first line is connected to the third line because A, as we said in the second line, is equal to sine X and B is equal to sine Y. So just substituting these values in, we finally prove this formula. On the top right corner, there are some addition formulas that we should know for trig problems in competition math. I encourage viewers at home to try and prove these formulas as well, although we will not be going over them in this lecture. Now, this slide shows some trig identities that we should know for competitive problems. Of course, we don't need to know them all, but they might be useful in some problems that utilize trigonometry. As shown, many of these identities utilize the reciprocals of sine, cosine, and tangent, which are shown in the center left side of the screen as cosecant, secant, and cotangent. Additionally, the majority of these formulas are derived from the basic sum formulas that we learned earlier. Okay, now let's move on to solve some competitive problems. Remember, there are other methods to solve the following problems with more than trigonometry, but we can solve them with the following solutions as well. I'll give you some time to read and solve these following questions, and I encourage viewers at home to frequently pause the video and follow along. I've prepared 4 problems to solve today, and 3 of them will be problems from math competitions. The last problem is a proof that we can derive using just the formulas mentioned above. Oh, I should note that the questions progressively get harder, so don't feel like you have to get them all right. And these trig problems can come up in many different forms, such as geometry or algebra. So this first problem is from 2014 AMC 10A, problem 22. And it states that in rectangle ABCD, AB is equal to 20 and BC is equal to 10. Let E be a point on CD such that CBE is equal to 15 degrees. And what is AE? So I'll give you a few moments to try and solve this problem, and I encourage viewers at home to pause the video right now and try to solve it. I think that was enough time to start your attempt. So let's move on to the solution. The first thing that we can note here is that we have to find AE. And to find AE, we can use DE. And to find DE, we can use CE. So if we set CE as x, then BE is the square root of x squared plus 100 by the Pythagorean theorem. Now, all we have to do is find sine 15 to know the answer. Firstly, with this sine addition formula, we can find sine 15 with sine 45 and 30, the basic values that we should memorize to solve trig problems. Then, as stated previously, we can find this ratio with the lengths of EC and BE. With this ratio and a bit of simplification, x is equal to 10 over 2 plus root 3. And with more simplification, EC turns out to be 20 minus 10 root 3. If you want, viewers at home, you can try to simplify this on your own as well. Finally, ED is equal to AB minus EC, which equals 10 root 3. Then we can finally find AE with the Pythagorean theorem on triangle ADE. And finally, we can see that our problem has the answer of E, which is 20. This is the second practice problem, and I'll give you a few moments to read this problem as well. This is from the 2022 AMC 12A problems, problem 17. And it states that suppose A is a real number such that the equation A times sine x plus sine 2x is equal to sine 3x has more than one solution in the interval 0, pi exclusive. The set of all A such that can be written in the form P, Q exclusive to the union of Q, R exclusive, where P, Q, and R are real numbers with P is less than Q is less than R, and we have to solve for p plus q plus r. So I'll give you a few moments to attempt the problem. If you're not finished right now, that's okay. And I think that was just to start attempting the problem. So the first thing that we're going to do is try to simplify the above equation to make this problem a bit easier for us. With the sign addition formula, we can find sine 3x with sine 2x plus x, which results in sine x times 4 cosine x squared minus 1. I encourage viewers at home again to try and simplify this on your own. Then we can manipulate sine 2x into 2 sine x cosine x, which is easily proven by the sign addition formula again. And this is also known as the double angle formula, but we use that right now. Then, with some intuition, we can simplify this equation by eliminating the sine x in all of the terms to get step 3 as shown. Finally, some of you may already see that 1 plus 2 cosine x is just a factor of 4 cosine squared x minus 1. So can we just divide the terms? Well, actually, it doesn't quite work that way. 2 cosine x minus 1 can also equal 0, so we have to consider this case as well. And therefore, cosine x is equal to a plus 1 divided by 2, and also negative 1 over 2. We manipulated the equation above, which was a times all of the signs, all the way back into these two simple cosine x equations. Oh, it's also useful to note that we could simplify sine x in all of the other terms on steps 2 to 3, because in the interval of x, when it is in 0 to pi exclusive, sine x is not equal to 1. Sine x is not equal to 0 at all, so we could just simplify it. So if we graph the cosine x functions that we got from step 4, we can find this Desmos graph that I drew as follows. Cosine x is drawn by the red graph here from the intervals of 0 to pi. And the black graph, which is y equals a plus 1 over 2, must meet the red graph at one other point, because if we read the solution, it says that this equation, which is just step 5 equation, has more than one solution in the interval 0, pi. But then something we can notice here is that when the black line just meets the blue line, which is cosine x is equal to negative 1 over 2, we can see that there's only one solution in the interval of 0, pi. And therefore, a plus 1 over 2 cannot equal negative 1 over 2 because there's only one solution. And therefore, we can see that because x is in the interval of 0, pi exclusive, cosine x is equal to the interval of negative 1, 1 exclusive. Now, because cosine x we said was a plus 1 over 2, a plus 1 over 2 is in the same interval as cosine x, and therefore, with a bit of simplification, a is in the interval of negative 3, 1 exclusive. And for the final step of the solution, we can say that if a plus 1 over 2 is equal to negative 1 over 2, then in the interval 0, pi, this above function has only one solution in the interval, and therefore a cannot equal negative 2. So finally, we get that a is in the intervals of negative 3, negative 2 exclusive, union of negative 2, 1 exclusive. So adding them all up, we can get a. Here are some important formulas for the next problems. A and B are derived from the sine addition and cosine addition formulae, where we just added sine x plus y and sine x minus y to get 2 sine x cosine y and subtracted them to also get the same result. Additionally, we can also subtract and add cosine x plus y and cosine x minus y to get 2 cosine x cosine y and negative 2 sine x sine y, respectively. The third C lemma is just derived from the functions of sine x and cosine x. And we can see that sine x is actually looks the same as cosine x, but just is shifted once more to the left, which is why cosine 90 minus x is equal to sine x. This is the third practice question and is from CMC 2009. These kinds of problems come up a lot in competitive problems, and so I'll give you a few moments to read the problem and solve it. Maybe you've started your attempt already, or maybe you didn't, but I'll go over the solution now. So the first thing we want to do is try to simplify this equation so that we can get the most simple value. So we can see that by C, which is sine x is equal to cosine 90 minus x, cosine 10, cosine 50, cosine 70 is equal to sine 20, sine 40, sine 80. And additionally, sine 10, sine 50, sine 70 is equal to cosine 20, cosine 40, cosine 80. And secondly, therefore, if we just add these two equations up, we can get the original equation just written in another form, which is sine 20, sine 40, sine 80 plus cosine 20, cosine 40, cosine 80. Then by b, which is cosine x plus y and cosine x minus y added, sine 20, sine 40 is equal to negative 1 over 2 times cosine 60 minus cosine minus 20, which is equal to negative 1 over 4 plus 1 over 2 times cosine 20. Then we can see that sine 20, sine 40, and that multiplied by sine 80 is just equal to step 3 times sine 80, which is equal to negative 1 over 4 sine 80 plus 1 over 2 sine 80 cosine 20. The equation from step 4 can again be manipulated into another sine 80 cosine 20 by a, where we can see that sine 80 times cosine 20 is simplified into 1 over 2 sine 100 minus sine 60 by a. Then simplifying the step 5 equation even more, we can see that negative 1 over 4 sine 80 plus 1 over 4 sine 100 minus 1 over 4 sine 60 is equal to negative 1 over 4 sine 60. This is because sine 80 is equal to sine 100, as we've stated before, because sine x is equal to sine pi minus x if we look at the function again. And therefore, negative 1 over 4 sine 60 is simplified into negative root 3 over 8. Similarly, cosine 20, cosine 40, cosine 80 can also be simplified into 1 over 8. And for this, I'll leave it up to the viewers in the viewers online or the ones watching this video to try and simplify it. And therefore, cosine 10, cosine 50, cosine 70 plus sine 10, sine 50, sine 70 can be simplified into 1 minus root 3 over 8, which is the final simplified form of the above equation. That was a lot of algebra for a trigonometry problem, but there are a lot of other competition problems that utilize these kinds of methods of calculation as well. Now, this is the last and final problem of the day. If you don't know what sigma notation is, just think of it as a compilation of additions. So if k is equal to 1 to n sigma, then that means that k sine alpha plus k from 1 to n is all just added. This is to say sine alpha plus beta plus sine alpha plus 2 beta plus etc. all the way to sine alpha plus n beta is added. I'll give you a few more minutes to try and attempt this problem. Now, if you get a general understanding of this problem, then I think we're good to go on to the solution. The first thing that we can do for this problem is just multiply out sine beta over 2 from the denominator in the right-hand side fraction. And this is because, as we've said earlier, the sigma notation is just a huge addition symbol, and therefore we can use the distributive property to make sine beta over 2 plotted into sigma k equals 1 over n to n to n. And therefore, if we do that, Sine beta over 2 times sine alpha plus k beta is equal to negative 1 over 2 cosine alpha plus k beta plus beta over 2 minus cosine minus alpha minus k beta plus beta over 2 by b. After that, again, this is a lot more algebra, but we can simplify the equation we can not simplify, but we can manipulate the step 1 equation to get cosine alpha plus k beta plus beta over 2 minus cosine alpha minus k beta plus beta over 2. And this equation is literally just the same equation from here. And this equation is, again, just moved into cosine minus alpha minus k beta plus beta over 2. If we utilize the property that's cosine theta is equal to cosine negative theta, and therefore this negative was distributed inside these cosines, and we use the property. After that, this equation can again be simplified into sigma k equals 1 to n, and this multiplied by this whole chunk of numbers, because again, cosine theta is equal to cosine negative theta, and therefore this is used as telescoping. This method of problem solving is called telescoping, where we add something and then we subtract something with the sigma notation. So if we plot the values of k equals 1 to n, we can see that 1 over 2 is multiplied by cosine alpha plus 1 over 2 beta minus cosine alpha plus 3 over 2 beta when we substitute k as 1 here. Then if we substitute k as 2 there, then we can see that cosine alpha plus 3 over 2 beta minus cosine alpha plus 5 over 2 beta is required. And we can see that this term here and this term here both cancel. And this canceling goes all the way until we set k as n, where that means that cosine alpha plus 2n minus 1 over 2 times beta minus cosine alpha plus 2n plus 1 over 2 beta is required. And therefore, because all of these other terms cancel out, again called telescoping, we can see that all of this sigma notation can be reduced down to this one fraction, where this one fraction is finally again reduced down to sign this huge fraction in the numerator on the fraction. We utilized the B lemma again for step 5. So just to give you guys a general recap of what we covered today, we covered first the basics of trigonometry, such as the functions of sine, cosine, and tangent. We went over the unit circles and radians and the role it plays in trigonometry. We plotted the trigonomic functions on the Cartesian plane, and we went over some trigonometric identities, which are useful in competitive problems. If you guys want to have some more challenges, I'd challenge you guys to try to study more about the functions of arcsine, arccosine, and arctangent. And if you're really up for a challenge, try to get the power series representations of the sine, cosine, and tangent values. Thank you, and that was my KGSEA lecture.